Hello and welcome to my YouTube channel Intromath. This is the third session for set theory, and in this session I'm going to discuss the properties of set theory. Some of the proofs will follow, and also at the end the amazing session with questions will follow. So keep watching. The first law here, a very basic law, an idempotent law. Idempotent law states that the union of the set A with itself is equals to A, the same set, and also the intersection of the set A with itself is also the set A. This is the first basic law, and this is called idempotent law. In algebra, we use commutative law very frequently. Which are the commutative laws in algebra? We know that 2 plus 3 is equal to 5. Also, 3 plus 2 is equals to 5. So, 2 plus 3 is equal to 3 plus 2. And also in case of multiplication, 2 into 3 is equal to 3 into 2. These are the commutative law. If the elements change their places, also the same result will follow. Not in case of subtraction and division. So commutative law, 2 plus 3 equals to 3 plus 2, and 2 into 3 is equals to 3 into 2. These are commutative laws in algebra. So in set theory, these are the commutative laws. A union B equal to B union A, and A intersection B equals to B intersection A. These are the very simple laws. So we are not getting the proofs here. The next law is the identity law. In identity law, these four laws are called identity law. A union S, S the universal set. A union S equals to S. A union phi the empty set equals to A. A intersection S equals to A, and A intersection phi equals to phi. Look at this Venn diagram. The whole set S, this is the subset. A is the subset of S. If we take the union, union means the elements either belong to A or belongs to S. So this is the whole set. A, also in A, those elements belong to A or S or both. So this is the whole set S. And in case of intersection, common elements are in A only. So A intersection S equals to A. If we take, since phi is the void set, there is no element in phi. So A union phi is must be A, and A intersection phi, since phi does not contain any element, so the intersection of phi with any set will not contain any element. So A intersection phi is also phi. So these laws are called identity law of set algebra. The next law follows complementary law. 5 laws are here. A union A complement equal to S, the universal set. A intersection A complement is the empty set phi. The complement of A complement is A itself. The complement of the universal set S is the empty set, and the complement of the empty set is the universal set. The last two laws are very simple to us. Now the first one, A union A complement. Look at this diagram. This is the whole set S, and this is the set A. The elements which do not belong to A belong to A complement. So this set outside A is A complement. If we take intersection of these two sets, we will get the whole set S. This is the union. So this is the whole set S. We prove the law here. And the intersection, if you take intersection, the elements in case of intersection, by definition we know that in intersection those elements belong to the intersection A complement, which belong to both A and A complement. Both A and A complement. Look at this diagram. There is no element belong to both A and A complement. These two sets are disjoint sets. So here A intersection A complement is 5. Now look, if we take the complement of the set A, this set is A, its complement is the outside A complement, and if we take the complement of this A complement, we will get again the set A. So the complement of A complement is equals to A. And simply the elements which do not belong to the universal set, there is no element, this is 5, and the complement of 5 is S. These laws are the complementary law set algebra. The next property is the associative law. In algebra, we use the associative law as like this. We know that 2 plus 3 plus 5 is equal to 8, and it is equal to also 2 plus 3 plus 5 is equals to 10. And if we first sum between 2 and 3, we will also get the same result. So this is the associative law in case of algebra. So in set algebra, the associative laws are like this: A union B union C equals to A union B union C. If we first take B and C union between B and C, this will yield the same result if we take the union in between A and B first. And in same case, in case of intersection. Here with the Venn diagram I have shown here, and it is for your homework. In case of intersection, you will calculate it in your home and comment if there is any difficulty. Here, look at these figures. These are the Venn diagram. Firstly, I have taken here B union C. B union C is this set, not this one. Either A or either B or C or both. So this is the B union C. And if we take the union in between A union, this set B union C, this is A union B union C in figure 2. Now I am taking here the union of A and B. This is the A union B figure, not this part. And if we take the union of C with this part, and this will yield this figure, A union B union C, A union B union C. Here, look in between figure 2 and 4. These figures are same. So from this figure and figure 2 and figure 4, we can easily state that this first law follows. A union B union C is equals to A union B union C. This is the associative law. In case of union and intersection will be the same result. Next, the distributive law. The distributive law, distributive property. Firstly, if we remember here, if we recall this property, 2 into 3 plus 5, this is equals to 16. Now 2 multiplied by 3 plus 5, we know that this is equals to 2 into 3 plus 2 into 5. This also yields 16. This also results 16. So here this is the distributive property in case of normal algebra. These results also follow in this set algebra. A union B intersection C is equals to A union B intersection A union C. And in case of intersection, A intersection B union A intersection C. This is the distributive law. I'm going to prove this distributive law now. I'm going to prove the first one. Since these two are the sets, two sets are equal when A is equals to B, when A is subset of B and B is subset of A. Okay, if A is subset of B and B is subset of A, then we can say that A is equal to B. Here these are two sets. I'm going to show here, I'm taking an element from this set and I will show that that element will be in this set. Then it will be subset of this one. I'm taking an element X from A union B intersection C. By definition, this implies that X belongs to A or X belongs to B intersection C. Again, I am using the definition here. So by definition, X belongs to A or X belongs to B and X belongs to C, the definition of intersection. Here I am distributing this one. X belongs to A or X belongs to B and X belongs to A or X belongs to C. Now, using definition, X belongs to A or X belongs to B. This implies that X belongs to A union B or union. Similarly, X belongs to A or X belongs to C implies that X belongs to A union C. Here again I am using the definition. X belongs to A union B and X belongs to A union C. That means X belongs to A union B intersection A union C. So A union B intersection C is subset of A union B intersection A union C. By definition here, I can say that A union B intersection C is subset of A union B intersection A union C. Now, if I take an element X from A union B intersection A union C, using the reverse process, the reverse implication, I can easily show that that element X will belong to A union B intersection C. Then this set will be the subset of this one, and with the help of these two, I can easily say that these two sets are equal. This completes the proof here. This is the sign, the completion of proof. We can use it. And I haven't used or and sign here. In future, I will use the sign or and which I have already stated in the first class. The next one is the law of absorption. Here A union A intersection B is equal to A and A intersection A union B equals to also A. I'm proofing the first one here. The second one is your homework. Here, look at this. A intersection B is this part. If we take the union of A with this part, then we will get this one. Look at this. A union A intersection B. A is this whole part, and with this A intersection B is this part. So from figure 2 it is clear that A union A intersection B is the set A itself. This completes the proof of law of absorption. Now the most important law in set algebra, the most important, I think, the De Morgan's law. The De Morgan's law states that A union B complement, A union B whole complement is equal to A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. I am proofing the first one. Second one is your homework. Also you will prove it by Venn diagram as your homework. I'm using the definition here. I've taken an element x from A union B whole complement. This implies that x does not belongs to A union B. A union B whole complement, x contains an element x, then x does not belong to A union B. This implies that x does not belong to A and x does not belong to B. Here is the union. Since there is does not belong to sign has been used, so A does not belongs to A and A does not belong to B. Here it will be AND. This implies that x belongs to A complement. If x is not in A, then x must be in A complement, and x belongs to B complement. By definition, I can say that x belongs to A complement intersection B complement. So by reverse implication, I can say that A union B whole complement is equal to A complement intersection B complement. This completes the proof here. And we can discuss some problems with the help of this set algebra if needed.